Welcome back. In this next section of the class, we're going to be talking about solutions. Now, solutions have a very specific definition that we're going to use when we use them in chemistry. And it's actually just a synonym for a homogeneous mixture. If you remember, homogeneous mixture means it's just the same everywhere. You can't be like, oh, over here there's this one part, over here there's this other part. They're all mixed together like sugar dissolved in water is a homogeneous mixture. Now, in general, when people talk about solutions, they're talking about liquids, usually in water, but it doesn't have to be. If you take a ring, perhaps, that's made up of gold and other metals, then that might be called a solid solution. But for the purposes of this class, we're going to talk about solutions as homogeneous mixtures. And there's two parts to a solution that we need to know about. There is the solute, and there is the solvent. Now, these definitions turn out to be very easy for what they are. The solute is what you have less of. And the solvent then becomes what you have more of. Very simple definition. So if I take sugar and I dissolve it in water, I generally have more water than sugar, unless it's Starbucks, at which point it might be more sugar than water. But in a case where it's less sugar than water, we have sugar is the solute and water is the solvent. And in fact, we're going to find that for most of the things we do in this class, water is going to be our solvent just because it's such an important solvent biologically and also in terms of climate and earth and things like that. So that's what we're going to see. But it doesn't have to be. You can take a little bit of water and pour it into a lot of alcohol, and there you have water as a solute and alcohol as a solvent. But for the most part, our solvents are going to be water. So the first question we have to ask is, we're going to start dissolving things into water. Why do things dissolve in the first place? So that's our first question. Why do salts dissolve? And let's go ahead and take sodium chloride as our example. Now, you may remember from a previous video that if you take sodium and chlorine, you mix them together, it forms this violent reaction because it's so favorable to have sodium chloride. Sodium chloride is extraordinarily stable. In fact, if you think about it, you take sodium chloride, you try to melt it. You ever put sodium chloride in a hot pan with some hot oil? You put it in, absolutely nothing happens. Why? Because those sodiums and those chlorides are so well attached to each other. Because remember, when you draw the structure for sodium chloride, it's these positive sodium ions next to these negative chloride ions. But it doesn't just stop there. Every sodium ion has several chloride ions surrounding it on every side. And every chloride ion has several sodium atoms surrounding it on every side. And it makes this one big structure, which we call a crystal. So if we're trying to take off, say, this sodium right here in the middle, my goodness, we have to take off all the chlorides around it and pull it out. That's a very difficult thing to do because those positive ions are very well attracted to those negative ions. So salt's extraordinarily stable. But then what do? We take a bit of salt, we go like this, we put it in water, and poof, just like nothing, it's gone. So what's so special about water that it can dissolve one of the strongest bonds on the earth as if it wasn't even there? So let's consider it. Well, what do we know about water? Well, if we take this and we're going to put this into a big vat of water. Now we've got a molecular size here, so we're going to have to scale up our water as well. Now water, we know, looks like OH. There's a couple lone pairs on that oxygen. And we also learned that the OH bond is polar and that oxygen is more electronegative than hydrogen. And so we actually have this small negative charge on oxygen and a small positive charge on hydrogen. Well, that small positive charge, let's say we're at the edge of the salt crystal and this water molecule comes up and sees this chlorine here. That hydrogen atom is attracted to that chloride atom and says, hey, how are you doing? I got myself a partial positive charge. You want to come hang out with me? And chloride looks around and says, hey, look, right next to me, I have a sodium with a full positive charge. Why would I want to hang out with you? You know, water's a little disappointed, but water is not one to give up. The nice thing about water is not only does it have these charges, it's also relatively small. So I'm going to shrink my water if my system lets me and make my water a little bit smaller. So I've got this water over here, and he's trying to interact with this chloride ion. And if one doesn't work, then he says, well, you know, what if I invite a friend? And you got another water molecule coming with its little positive, slightly positively charged hydrogen and says, hey, now we've got 2 slight positive charges. Does that tempt you, Mr. Chloride? And he looks around and says, 2 slight positive charges. I got a full positive charge over here. You guys go away. But water, remember, this is in 3 dimensions. And so not only can we do this ones that are flat that we can draw, but we can do ones in front of the chloride. We can do ones in back of the chloride. And essentially what happens is water eventually sends in enough positive ions over there to overwhelm the chloride ion and make him say, well, you know what, maybe I will go with you. And as soon as he separates from that chloride, another water molecule or 2 can come in on the inside there. And this chloride ion floats off into the water, happy as can be with his water molecules. Now, what does he do? He exposes a sodium ion. And so what does that sodium ion do? I'm going to draw it up on top here because there's a little more space. That sodium ion, how's he going to get lured away? Well, he's going to get lured away because water, has this slight negative charge on the oxygen. Comes up to sodium and says, I got a slight negative charge, and sodium goes, I don't care. But you build up enough waters, and all of a sudden that sodium can then run away with the water and float off like that. And this happens at an incredible rate. You take salt, you go like this, you sprinkle it in, stir it, and boom, just like that. And by the way, when you see salt, right, you're already talking about 10 to the 20th, 10 to the 21st atoms of sodium or chloride, a huge amount. But it dissolves just like that because this process of water coming in and tempting these ions is a very quick process. And that's how it does. It just picks at it, picks at it, picks at it until it's all gone. But what happens as a result of that? What happens as a result of that is that when you take salt water and you dissolve it, you put in NaCl, all these guys attached to each other, but what you end up with is a solution where the sodium ions and the chloride ions are happily surrounded by their water molecules. I'm drawing probably a few more than there are. Happily surrounded by their water molecules, and they don't talk to each other anymore. The sodium doesn't even care whether the chloride is there because he's so happily balanced out by the water molecules that are surrounding him. The chloride up there in the corner doesn't really care whether the sodium's there at all, doesn't even notice him. Right? Now, occasionally as they run along, they bounce into each other and kind of from far away they say, hey, how you doing? They're like, yeah, I don't need you anymore. And so when we dissolve salt in water, we don't get salt anymore. So if we take sodium chloride solid and we dissolve it in water, sometimes you put water on top of the reaction arrow to say you're dissolving it in there, you end up with sodium ion and chloride ion separated from one another. Not sodium chloride together. There's no sodium chloride in salt water. There's sodium ions and chloride ions that are acting independently from one another. Now remember, this aqueous, if you recall from our last chapter, means dissolved in water. And that's exactly what our ions are. They are ions that are dissolved in water. Same thing for any other salt. You want to take potassium fluoride. When you dissolve that in water, you get potassium ions and fluoride ions, but no more potassium fluoride. You want to take sodium carbonate and put that in water. You get sodium ions and carbonate ions. No sodium carbonate left in that water. So all of these things, when we dissolve these salts in water, they separate out and they act independently. That's going to be really important later on when we talk about how do we predict solubility, because not all salts are soluble. So how do we predict solubility? We have to know about how they behave. And that's how they behave, independently once they dissolve. Now, that's ionic molecules. That's things where there's a positive charge and there's a negative charge. But there's also another class of things that don't form ions that still dissolve. And a great example of that is one I mentioned earlier, which is sugar. Now, we all know sugar dissolves in water. That's why Starbucks is in existence, not because they have great coffee, but because sugar dissolves in water and it tastes good with all that sugar. I like my sugary ones, I have to say. And so why would this one dissolve in water? I'm going to tell you, and you can just trust me on this one. You can Google it if you don't trust me, that when sugar dissolves in water, it does not make ions. There's no positive part of the sugar and negative part of the sugar that break apart for water to come and look at. So how can a water molecule look at this sugar molecule and convince it to go away from another sugar molecule? Well, the general principle we're going to use here is a chemical principle that says like dissolves like. That if you want to dissolve something, if you want to attract something, the best way to attract it is by attracting something that's very similar to it chemically. So in the last example, we looked at water, which was highly polar and looked very ionic. And that's why it was able to attract those ions and say, hey, come with me because I'm kind of ionic. Like dissolves like. But how does that apply in the case of sugar here if it's not ionic? Well, what we want to look for in the sugar molecule, is there anywhere in this molecule that looks like water? Because like dissolves like. So looking at that, do you see anything in there that looks a little like water? And of course I do, because I'm teaching this class, and if I didn't, I'd be in trouble. So I look right here and I see an OH. I said, hey, there's OHs in water, right? Water looks like this. And so this OH and this OH look an awful lot alike. And what actually happens, I drew this kind of backwards, is another water molecule comes up, and the negative oxygen from one OH is attracted to the positive hydrogen from an oxygen. And these guys are attracted to each other as well. And all of a sudden, there's a little bit of attraction here between the water and the sugar molecule. Now, is that enough to get it to break apart and come off into the water? No, we need more. But hey, look, there's another OH that looks a little like water. And hey, look, there's another one, and another one, and another one. And in fact, there's a bunch on here. There's also other parts that look not quite as much like water, but a little like water, like this bond right here. Now, we're going to learn how to read these structures later on in the class, but right now what you just need to know is that little intersection there where there's nothing labeled is a carbon atom. So we've got a carbon bonded to an oxygen. That's a polar bond. We know that oxygen's more electronegative than carbon. So there's a little bit of charge exchange there, a little bit of unequal distribution, and the water's attracted to that as well. So when we start to circle all the different spots in this molecule where the water is attracted, boy, there's a lot of them. And you start getting 5 or 6 waters around each one of those, and all of a sudden there's enough net water attraction that one of those sugar molecules can just come right off and be surrounded by water and be very, very happy. And again, this happens, boom, almost instantaneously. It's crazy how quickly it happens. And it's because like dissolves like. Other examples of that, if you've ever tried to get stickers off of something, like you peel off a sticker and it leaves all that goop behind. Water doesn't cut it. What you want to do is you want to put more oil on there. Why? Because those stickers are primarily made up of oily type of substances. And if you want to dissolve them, you want to dissolve them in oil. And then you can wash off the oil. It works really well. Or if you're looking at a whiteboard and somebody left some marker up there and you can't erase it anymore, you try the little dry erase and nothing happens. You don't have any of that chemical around. What are you going to do? Well, the easiest thing to do is actually just take another Sharpie and just take this guy and just write over the stuff that's been there a long time. Because what's one of the most things that looks a lot like Sharpie? Sharpie. And so if you want to dissolve Sharpie, dissolving Sharpie in Sharpie is a pretty good idea because like dissolves like. And we'll see examples of this in all sorts of things as we talk about the properties of molecules. Is that if you want something to be dissolved in something else, you want to make it look like that. Now, that brings us to things like oil. Like oil, what does oil look like? Because if you take oil and water, right? You try to mix them, what you get is oil on top and water on the bottom, and they don't mix. Now, why is that? A lot of people will say, hey, oil and water don't mix because they repel each other. You'll hear people say that term, but it turns out that's not true. Oil and water actually attract each other, but only a tiny, tiny bit. They look nothing alike. Oil primarily is a chain of a bunch of carbon atoms. I'm not going to show all of them, with hydrogens on them. Now, there's sometimes other things in oil as well, but it's primarily just carbon and hydrogen, carbon and hydrogen, carbon and hydrogen, carbon and hydrogen. And we know that none of those bonds are polar because carbon-hydrogen bonds aren't polar and carbon-carbon bonds aren't polar. So that oil molecule looks absolutely nothing like this extremely highly polar water molecule that we've got floating around next to it. So when water looks around and says, hey, who do I want to hang around with? He's going to say, other water molecules because they're like me. And when the oil looks around and says, who do I want to hang around with? He's going to say, well, I want to hang around with other oil molecules because they look like me. And the oil and water separate not because they don't like each other, because they repel each other. No. They just like themselves more. Water likes water more, and oil likes oil more, and so they stay with each other. So that's actually what you get when you get oil and water. What do you do if you want to dissolve oil? Well, you dissolve it in something else that looks like oil. So oil tends to be these very, very long chains of carbon, hydrogen, carbon, 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 carbon. If you want to dissolve it, you can use maybe a smaller chain of just carbon, 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 hydrogen. And as long as it's a non-polar molecule, it'll dissolve the oil pretty well. So if you took, I don't know, olive oil and gasoline, they would probably dissolve pretty well because gasoline is made up mostly of carbon, 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 hydrogen. Right? And so you'd be able to dissolve those two things into each other because like dissolves like. But then there's magic. There's this magic thing called soap. What dissolves in soap? It's like almost everything, right? Oil dissolves in soap, salts dissolve in soap, water dissolves in soap. What is magical about soap? The really cool thing about soap is I'm going to draw the carbon hydrogen things just like this, and you'll see why later in the class. But there's a bunch of carbon hydrogens. So you get this non-polar part of the molecule. Then the details don't matter, but at the end of the molecule, what they do is they put a polar part. And so this molecule actually has some polar parts on it and some non-polar parts on it. And when it's trying to dissolve soap, it hangs out its little non-polar tail and says, hey, I'm some non-polar, come hang out with me. And they're like, sure, we'll hang out with you. And when it's trying to dissolve polar things, it hangs out its polar side and says, hey, I'm polar, come hang out with me. They say, sure, I'll come hang out with you. And that's how soap can actually do both, because it has both the polar and the non-polar parts of it. It's a really neat chemistry that goes on in some of the very simple things in our life. But all of it's based on like dissolves like. So that's why things dissolve, because like dissolves like. So here's a question for you. Which molecule below do you think would be most soluble in water? So I want you to take a moment. This is a really good one to just pause the video and stare at those molecules for a minute and think to yourself, which one of those looks most like water? Okay, pause. No, pause. It's the button right there, about right there, pause. Okay. Good. So you paused, you thought about it, and you said, well, water looks like this. So I want to find something that looks most like that. And when I look at this top molecule, I don't see anything that looks like that. Right? That one has no O's, no H's, no polars, no nothing. So this is probably not a very good candidate. When I look at this second one, I see two parts here that look like water. That's a good sign. There's a big part in the middle that doesn't look like water, but there's these two parts on the end that look an awful lot like water, and that's a very good sign. What about this third one? Well, that doesn't quite look like water, but it does have a couple little polar molecules in it, so maybe that's a little like water. And it is, it's a little like water because it's polar, but not so water-like. You look at the one at the bottom, it has one part that looks an awful lot like water. So if water's going around and trying to find someone to hang out with, do you think he's going to hang out the one that has two copies of him, one copy of him, or kind of this fuzzy copy of him? And certainly the water's going to go for the one with two copies, and this one is going to be the most soluble in water. So look at this. I mean, these are molecules that you aren't really sure what they are, you don't know what they do, but you can start to predict things about their relative solubilities. This works in medicines and other things. You can start to look at molecules and think about, well, what's the likelihood that this is going to be soluble in water? And you can do some really neat stuff just thinking about like dissolves like. Our next subject in talking about solutions is a set of solutions that are called electrolyte solutions. What is an electrolyte? Well, for those of you who go out and buy yourself some Gatorade, hopefully you know what an electrolyte is, because you're paying for it, right? You're like, hey, it's the stuff that gives me energy, it replenishes my body. But it turns out electrolytes have a very simple definition. They are ions dissolved in water. Very simple. Ions dissolved in water. Which means if I took some salt and I took some water, I poured the salt in the water, I stir it up, I could sell that to you as an electrolyte solution. Now, of course, Gatorade actually has electrolytes in it that try to mimic those that you use in your body and those that are already in your body so that when you exercise and lose them, it'll replenish them. There's some debate as to whether or not they work in the literature. I'm not going to go there right now. I buy those for my children, especially when they're sick. They're great, and they're a whole lot cheaper than Pedialyte. All right, so electrolytes, ions dissolved in water. And, excuse me. So we wrote things like that before. We said, hey, we've got sodium chloride, solid. We're going to dissolve that in water, and we get sodium ions and chloride ions. And that's what we might write as a balanced reaction for dissolving in water. Some people will even kind of skip the solid part, and they'll just say, oh, I've got some potassium fluoride. It's aqueous, and when it falls apart into potassium ion and fluoride ion that's aqueous. And any of those would classify as an electrolyte solution. The important part is that you have charges present. And remember, anytime you have a positive charge present, nature loves balance, and you've got to have an equivalent negative charge present. And that's how we actually made our ionic formulas and things like that in our previous work. That also applies here. So why do we care about electrolyte solutions? Well, it turns out electrolyte solutions do this neat thing called conducting electricity. Now, the first question to ask yourself is, what is electricity? Some of you pay your electric bills. What are you paying for? You're like, well, I'm paying to be able to turn the lights on. Great. What happens when you turn the lights on? What is actually coming through that makes those lights turn on? And it turns out what you're just paying for, those little wires that come to your house, right? You've got the big wire here. You've got your house here. And this wire comes into your house. What are you actually paying for? What you're paying for and that they're sending over is electrons. So they send electrons to your house. You use them, and it turns out you actually send those electrons right on back to the power company. So they're not actually selling you the electrons. They're renting you the electrons for a period, and then you just give them back. It's a great business to be in, right? Here, I give this to you, you pay me money, and then you just give it right back to me when you're done. The difference is these electrons, when they come in, have high energy. You use that energy in your house to plug in your phone to turn on your lights. And the electrons you return have low energy, and you're paying the power company to put energy into those. But that's all electricity is. It's the movement of these electrons through wires. But it turns out electricity is not limited to electrons moving through wires. And we know this because, of course, everybody knows that you never want to accidentally drop your hairdryer into a bathtub, because you'd electrocute yourself, because the bathtub, the water in there, is going to conduct electricity. And there's no electrons floating around in water. So how is it that water can conduct electricity? Well, in the tap water that we have, there isn't just water. There's water, and there's a bunch of dissolved ions in it. There's calcium ions, there's potassium ions, there's sodium ions, there's chloride or chlorate ions, depending on what's going on. So there's lots of ions in there, and these are the things that can actually conduct charge or electricity by moving around. So you drop your hairdryer in there. It's not the water that's actually conducting electricity. It's the ions that are in the water that are conducting electricity. And there's some terminology we use. There's some terminology we use for talking about how things conduct electricity and whether or not they do. And we use this terminology called strong and weak electrolytes. Sorry for the interruption there. A strong electrolyte is one that dissolves in water, making 100% ions. And those are things that we've been talking about so far. Sodium chloride. When you put that into water, you stir it up, all of it dissolves. There's sodium ions, chloride ions. There's no sodium chloride left in water. And that would be what was considered a strong electrolyte. And as you can imagine, a strong electrolyte can conduct electricity really well, because there's lots of ions available in a strong electrolyte to move around and conduct that electricity. If we were doing a normal lab, we would have done a demo, and we would have actually seen this apparatus that you can stick a light bulb with some exposed wires into a solution of sodium chloride, and it lights up really, really well. On the other hand, there's also things called weak electrolytes. And you can guess it's probably the opposite of a strong electrolyte. So these ones also dissolve in water, but they only make a few ions. Most of them don't make ions. And you're like, well, how can that happen? We just talked about how the water dissolves things. It turns out that a lot of acids, so acids that you might run across, vinegar is acetic acid. Most acids, when they dissolve in water, stay as an acid. Now, we're going to use HF down here as an example. I'm always amused that books and things like that, people, when they talk about these things, they use hydrofluoric acid as an example of a weak acid. In fact, you'll use it all sorts of places. And I've always thought, well, why hydrofluoric acid? It's a pretty nasty chemical. I mean, if you breathe too much hydrofluoric acid, it causes all sorts of respiratory problems. If you get it on your skin, it dissolves in and starts replacing structures of your bones. And I mean, it's a really, really nasty chemical. So why does everybody use that as the example when they talk about weak acids? And I finally figured out that the reason is that it's only 2 letters. And so it's really easy to write. So here we go. I'm going to do it too. Hydrofluoric acid, HF. When you put HF into water, it turns out that in the water, most of it stays as HF. But a very small fraction of it does break apart into H plus and F minus. We'll talk in the next chapter about how acids break apart. But it breaks apart into H plus and F minus. So there's a few ions around, not very many. Not the same as if you put in the same amount of sodium chloride, where all of it makes ions. And so what do you think about a weak electrolyte? Is it going to conduct electricity? Well, yes, because it has some ions present, but probably not very well. And so a weak electrolyte is a weak conductor of electricity. And again, mostly these are acids, so most of our weak acids, we'll see that goes in the next chapter, and also things like urea. Urea is also another common one. Now, what happens to things like sugar? Dissolves in water, and I said, hey, no ions when you've got sugar. So what happens there? There you have what's called a non-electrolyte. And a non-electrolyte, and I put a dash there, but you actually don't need one. It's actually one word. A non-electrolyte dissolves in water and makes no ions. So no ions whatsoever. All the sugars, sucrose, fructose, glucose, they all do this. And so, and I actually said the wrong thing just a minute ago. I said urea was a weak electrolyte. Urea is a non-electrolyte. I apologize for that. So urea also is on that list. Now, what would happen if I tried to conduct electricity in this solution and I had just water and sucrose in it? Well, there's no ions present, and so it turns out that that thing would not conduct electricity. And so a pure sugar water solution would not conduct electricity. Now, you can't try this at home, really, because you don't have access to pure water. The water that comes out of the tap already has some ions in it. But if you had access to pure water and you put sugar into it, then no, it would not conduct electricity. So that is the concept of electrolytes. Our last introductory concept in solutions is the concept of equivalence. Now, I have to admit, as a chemist, I went out, I did chemistry, I did lots and lots of chemistry, years of chemistry, and it wasn't until I came to Mount Sac and I taught this chemistry class that I ever heard of the unit equivalent. And I'm like, dude, they gave me a PhD in chemistry and I've never heard of equivalence. How important can this unit be? And I finally found out because I had a child in the hospital and I was looking and listening. And equivalents are used in the health field a lot. They're a very common unit that you see in the health field. And in fact, equivalents aren't what you usually see. You see milli-equivalents per liter, but we'll talk about what that is in a moment. The purpose of equivalence is sometimes it's less important to talk about how much of something you have. I've got 5 grams of this or this concentration of that, but to talk about what the charge is in what you have, because a lot of the processes in our body depend on charge equivalence. And so what an equivalent is it's a way of talking about the charges that are present in something without actually having to talk directly about the charges. And you'll see what I mean in just a moment. The basic definition of an equivalent is 1 mole of something is equal to X equivalents where X is equal to the charge on your something. You're like, Professor Clements, you just confused me. You'll understand in just a sec. It's actually pretty easy. Sodium ion. Sodium ion has a +1 charge. So 1 mole of sodium ion is equal to 1 equivalent. Most people will shorten that to EQ, so I'm going to do that, of sodium. Why? Because a +1 here becomes a 1 here. You can guess what's coming. If I've got sulfate ion, number 8 being SO4, 1 mole of sulfate ion, we're going to take that 2 and we're going to put it here. Now, do we put the negative? And the answer is no. All equivalents are always positive just by definition. Somebody just said, hey, let's make sure all equivalents are positive. 2 equivalents of sulfate. If you had aluminum ion, Al3+, 1 mole of Al3+ is 3 equivalents of Al3+. So very easy. 1 mole of anything charged is equal to the equivalence of that equal to its charge. Sodium has a +1, so it's 1 equivalent. Sulfate has a -2, so it's 2 equivalents. Aluminum has a +3, so it's 3 equivalents. And we'll use that to talk about how to use that unit of milliequivalents per liter to figure out how much of something we have in solution. So we're going to go ahead and do that, because quite honestly, the only time I'm going to have you use equivalents in this class is to do these types of conversions of milliequivalents per liter to either moles of something or grams of something. And the best way to figure that out is with an example. So we're going to have a solution that has 47 milliequivalents of sodium per liter and 47 milliequivalents of carbonate ion per liter. We give 100 milliliters of the solution, and we want to know how many moles of sodium and how many moles of carbonate were delivered. Now, it turns out you can start with any of the numbers there. You can start with the 47 milliequivalents per liter, or you can start with the 100 milliliters. If you remember, at the very, very start of the class, one of the things that you might have learned is that if you start with 1 unit and you end with 1 unit, that's the easiest type of conversion. If you start with 2 units and end with 2 units, that's an easy type of conversion. If you start with 1 unit and you want 2, or you start with 2 and you want 1, then you have to do things a little bit different. So what I'm going to do is I'm going to go ahead and start with my 100 milliliters of what, right? Of IV solution. So always got those helpers in there. Don't leave out the helpers. The helpers are important. So we've got 100 milliliters of IV solution. And what are we trying to figure out? We're trying to figure out moles of sodium ion. And boy, wouldn't it be nice if I could do that in one step, but I can't, because my conversion would be moles of sodium ion for every milliliter of IV, and I just don't have that information. The only information I have here is milliequivalents per liter. And so I look at that and I think, well, that's in liters, and I've got something in milliliters. So maybe my first step is going to be to convert to liters. So let's go try that first. We're going to take my milliliters, and we're going to convert that to liters. And in case we wonder, it's liters of IV fluid. Normally I wait till the end to fill these in, but this one I'm just going to go ahead and do. We know that there's lots of little milliliters in 1 liter. So 1,000 milliliters in 1 liter. Okay, so we've now got liters of IV fluid, but we don't want liters anymore. That's a volume unit. We want moles, which is related to quantity. So how could we take that liters over to some sort of quantity? Well, we've got a unit up here that relates liters to milliequivalents. Let's try that. What do we know has to go on the bottom? Hopefully, you came up with liters of IV fluid so that it cancels. Okay. Now what's going to go up on top are milliequivalents. It's sometimes tempting for people to put just like a 1 on the bottom and put milliequivalents per liter on top, but we don't generally do that. Our conversions almost always just have 1 unit on top, 1 unit on the bottom, not a fractional unit on the top or a fractional unit on the bottom. Now, where does that 47 go? Don't memorize it goes on top or bottom. Memorize that numbers stay attached to their units, and that 47 is attached to milliequivalents. And so he goes there. Per liter means per 1 liter. So now we've got milliequivalents, and we're still not there, because moles, Gosh, well, moles, how does moles relate to equivalence? Oh yeah, there is. The definition of equivalence has to do with moles. But I need equivalence, and I've got milliequivalents. So what's my next step? I need to get rid of those milliequivalents. And I forgot my helper there, milliequivalents of sodium. And I want to go to equivalence of sodium. I don't want milli anymore because I don't know my definition between milliequivalents and moles. I just know my definition between equivalents and moles. And again, we know that the milli is just 1,000, so a lot of little tiny milliequivalents in one big equivalent. And then lastly, we're going to put this parentheses over here, and we're going to get rid of equivalence down here. And do we know how to do that to moles? Absolutely. We know the relationship between moles and equivalents. For sodium, since it's got a positive 1 charge, it's 1 mole is 1 equivalent, and you just get a 1-to-1 right there. Now, you plug that into your calculator, and what do you get? You get 4.7 times 10 to the minus third moles of sodium ion. Now, I could also ask a question where I ask you to find the mass, and all you do is one more conversion after that. Use the periodic table to look up the atomic mass of sodium, multiply by that, and then figure out how many grams of sodium ion you have. How about the second part of the question, which is how many moles of carbonate were delivered? Well, anything going to stay the same? What's going to be different? Let's look at each step of my equation here. Is this step going to be any different? No, because that has nothing to do with carbonate. Is this step going to be any different? Well, the letters are going to be different because I'm talking about carbonate. But luckily for us, the concentration of my carbonate is the same as the concentration of my sodium. And so that's not going to change. Is this one going to change much? The answer is no. So the only one that's going to change is this last one. So all three of these are going to be the same. And we just need to change this last conversion. And we've got equivalents of carbonate and moles of carbonate. And if you can't remember what goes where, oh, you can always write down the definition. 1 mole of carbonate, it's always 1 mole, is 2 equivalents of carbonate. And then remember that numbers stay attached to their unit. So this 2 goes down here, this 1 goes up here. And we essentially get half this number, or 2.4 times 10 to the minus third moles of carbonate. So that's how we do milliequivalence problems. Anything that I ask you to do on a quiz or test, very, very similar to what we've done here. Starting with an IV volume and trying to figure out moles or grams of something at the end. So one last question on equivalence. How many equivalents of charge do 4.0 moles of phosphite ion have? So that's a good one. Pause again. See if you can come up with the answer. All right, what'd you come up with? Well, phosphite, first you have to know what is phosphite, PO3 minus. So we know that it's got a -3 charge, which means that 1 mole of phosphite is 3 equivalents of phosphite. But we don't have 1 mole, we've got 4 moles. So 4 moles, what did I have to do? I had to multiply by 4. I got to multiply by 4 on the right, and I get 12 equivalents of phosphite. And so down here the answer was E, 12 equivalents of phosphite in 4.0 moles of phosphite. So that's our introduction to solutions. We now know what a solution is, what a solute and a solvent is. We know a little bit about why things dissolve, and we learned about electrolyte solutions and their definitions, and also about the unit equivalence. And we're going to continue on learning a bunch of new things and numbers for solutions as we go forward. Thanks.